Greetings and welcome. In today's video, we're going to talk about the probability of compound events. And what we mean by compound is we have multiple events occurring either in succession of one another or simultaneously, and we're going to have to find the probability of both occurring successfully at the same time. So the probability of two events, if I have two events A and B, and they're independent of one another, all right, so this is key, then the probability of both events occurring successfully is the product of each individual probability. So this is similar to when we calculated the number of ways two separate independent events could occur back in combinatorics, where I would just simply multiply, right, those separate possible number of ways. And similarly, that happens here with probability. So let's look at our first example. So what is the probability of drawing a prime from a deck of 52? So let's see. So I want to figure out, well, first of all, what are the prime cards in a deck of 52? By prime, I mean prime numbers. All right, I'm a math teacher. So the prime numbers in a deck of cards would be 2, 3, 5, and 7. So there are a total of 4 prime numbers in each suit, and there are 4 suits to consider. So when I multiply those, I get 16. So the probability of prime is going to equal the number of successful cards that would work for us is 16. The total number of cards is 52. All right. And now what I'm going to do is calculate the probability of this separate event. Right. So the probability of rolling an even on a 12-sided die. The even numbers on a 12-sided die would be 2, 4, 6, 8, 10, and 12. So the probability of getting an even, there are 6 outcomes there that are successful, 12 possible ones, and that's what I would get. And I guess I might as well reduce these. This reduces to 1/2, a 1/2 chance, and this 4 goes into 16 4 times, and into 52 13 times. All right, there's 13 cards per suit. There's 4 suits, so that's the way I remember that. So if I want to now calculate the probability of both occurring at the same time, so the probability of prime card and an even roll, 1d12, it is going to equal the product of each of these probabilities, right? So that'll be 4/13 times 1/2, and I believe I can cross-cancel. The 2 goes into 2 once and into 4 twice, and I'm going to end up getting 2/13 as my answer. Right? So now I can find the likelihood of both of those events occurring simultaneously, or in succession. I guess you didn't have to pick the card and roll the die at the exact same moment in order to do that. All right, so let's look at another example. What is the probability of drawing 2 cards with replacement and getting 2 diamonds? All right, so we have 2 separate situations. Now, the fact that I'm replacing the cards, all right, so it's like I draw a card from the deck, I look at it, and then I put it back in the deck, shuffle, and then draw again. So these are in fact independent events, right? So the first event did not have an effect on the second. So let's see. Let's figure out what the probability of first card diamond is. So let's see. There are 13 diamonds in the deck of 52 cards, and that can reduce to 1/4, right? Or I could think of it as 1 out of 4 suits in the deck are diamond. And then let's figure out what's the probability second card is diamond. Pardon my lag there. And that's exactly the same situation because I took that first card, put it back in the deck, reshuffled, so it's the same probabilities, right? 13 out of 52 or 1/4. And then if I want to find the probability of both cards diamond, I will just multiply these probabilities. 1/4 times 1/4. So there's a 1/16 chance that when you draw two cards from a deck, that they'll both be diamond. So that is for independent events. Let's consider, however, what about when our events are dependent on one another? So if two events A and B are dependent, then the probability of both events occurring is the product of each individual probability. And notice there's a subtle difference here. So I find the probability of event A and I multiply it by the probability of event B after A has already taken place. Alright, so chances are the likelihood of B occurring has somehow changed because A happened. Alright, so let's continue with our deck of cards situation. So in a deck of cards, what is the probability of drawing a face card, not replacing it, and drawing a 5? So probability of face card. So face cards are jacks, queens, and kings. Alright, so aces aren't faces. And there are, let's see, so there's 3 face cards per suit, 4 suits, so that's a total of 12 face cards in the deck, right? So 12 out of 52 are face cards. Let's reduce this. I think 4 goes into both of those. So that's 3/13 of the cards are face cards. And I guess I also could realize 3 out of every 13 cards in a suit are face cards, right? So that makes sense. Now, I have not replaced it. Alright, so there are fewer cards in the deck. So now I'm going to calculate the probability of drawing a 5 after a face card. Alright, so this deck is short 1 card. Alright, so how many 5s are in the deck? Well, there are 1 per suit, 4 suits, so there are 4 5s in the deck. And I want to point out that all 4 5s are still in the deck. It's not as if one was removed when I took this face card out, right? And then how many cards are still in the deck? There are 51 cards in the deck. Alright, so to find the probability of both events occurring, so I could say face, then 5, I guess, is the way I could describe it. I will multiply these probabilities. So 3/13 times 4/51, and I do not believe this will reduce. 12 over, and let's see, 13 times 51 is 663. And there is my probability. Actually, wait a minute. I just realized, yeah, it does reduce. Let me actually skip back here. It's easier to cross-cancel it. 51 is divisible by 3, my bad. 3 goes into 3 once and into 51 17 times. Yeah, that's not one you'd necessarily notice. I didn't in that instance. So 1 times 4 is 4. 13 times 17 is 221. There we go. There's a reduced answer. So there's the probability of this occurring one after the other without replacement. So because there was no replacement, that's why this was a dependent situation, right? And we saw that in the change in the denominator. Let's see, last example. When drawing 2 cards from a deck, what is the probability of getting an even and a queen? Alright, so this didn't say if it was 1 card after another. I mean, I could reach into the deck, grab both cards simultaneously. But I want to say that this is the same as drawing an even then a queen without replacement. Alright, so this is similar to the situation we saw earlier. So I'm going to figure out, first of all, what's the probability of getting an even. Right, and the reason this is true, that without replacement, it's not possible to draw 2 cards from the deck of 52 and then be holding the same card twice, right? They'd be 2 separate cards. That's like a physical impossibility. So that's why I could also think of it this way. So let's see, what's the probability of an even? Well, number of even cards. Let's see, the evens are 2, 4, 6, 8, and 10. right, for the numbered cards. So that's a total of 5. 5 times 4 suits is 20. So there are 20 even cards in the deck, 20 out of 52. Both of these are divisible by 4. 4 goes into 25 times and into 52 13 times. And now let's figure out the next probability, which is the probability of a queen after we drew an even. Okay? So the deck has changed, right? There's one less card in it. So how many queens are there? There's 1 per suit, 4 suits, so 4 queens, right? And there is 1 less card in the deck, so 51 is what we've got. So to find the probability of both things occurring, even and queen, right, when drawing 2 cards, I'm just simply going to multiply these probabilities. So 5/13 times 4/51, right? So that's going to equal 20 over 13 times 51 is 663. I think I did that earlier, didn't I? Yeah. And that does not reduce. So that would be my answer.